where we are, and we started acids and bases. We started talking about the idea that acids and bases are typical of sort of simple chemical reactions in which you have to think about the interaction between maybe 2 or maybe 3 different components. And you've all seen this stuff before on a very basic level, a very simple level. Now we have to expand it so that you can look at any big organic molecule and have something to say about its acid and base properties so we can start to use it. And acids and bases in organic chemistry are everywhere, so you must get this immediately, and we will use them to do different jobs. We will use acid-base chemistry to make things more reactive. We'll use them as maybe a preliminary type of process to make something else more reactive, and then something else happens. So this is the first idea of mechanism, the first idea of how chemicals come together to actually interact. A lot of it is very straightforward. A lot of it is find the lone pairs on one piece, find the delta plus part on the other piece, and connect them together. Keep an idea on the octet rule, don't be breaking that, and we should be okay. We define very quickly the idea of the acid and the base. Very simply, one is a proton donor, one is a proton acceptor, but as we work our way through the class, not all acids have protons. They don't have to have a proton to be an acid. They have to be an electron acceptor. That will come a little bit later. But at the bottom, we've got some basic definitions now. An acid is one component, a base is the other component. And on the right-hand side, we've got the opposites. We've got the conjugate base and the conjugate acid. You must be happy with those relationships very quickly so that we can start to worry about equilibria. We can start to worry about whether an equilibrium is formed, and if it is the left-hand side better or is the right-hand side better? Is the equilibrium constant K greater than 1 or less than 1? So what we'll do today is learn some numbers. We'll think about transitioning from water, which is pretty much all the acid-base chemistry you've ever done in the freshman labs where you titrate stuff, into organic materials, into organic solvents where there's no water around, and we have some sort of opportunity now to expand the sort of alphabet for acid and base chemistry. So I drew this, so we have this on the slide. This is really your first example of a mechanism, a very simple, what we'll call a bimolecular mechanism in which 2 pieces come together and give you some products. We are now using the green arrows, the little curved arrows, to describe electrons and to describe the idea that in this process, a lone pair from that base is going to be used to form a bond. So that green arrow is describing a bond forming. And we have to keep an eye on the octet rule. Very simple in acid-base chemistry, you have to push away from the A atom, you have to push away from the hydrogen because it can only handle 2 electrons. So 2 electrons must go in and 2 electrons must go out. So there's a process happening here, and this is dynamic. This is chemical change. You can see now that this first green arrow is describing a bond forming. In other words, a lone pair from B is being used to become a bond pair. And the bond pair between H and A is going towards A to form the lone pair. So there's definite change here in terms of orbitals overlapping and the chemicals changing to become products. Well, we'll have to expand this very quickly. And again, we're not here Monday. It's terrible that we're not here Monday. We need to be happy with the very simple ideas so we can expand into a much bigger universe and look at much more complicated molecules. So down here, I would hope by now that people who've passed freshman chemistry can look at that and tell me pretty quickly that hydroxide is the base. It certainly isn't the acid. You're not going to take off that proton even though it does have a proton. It's just not acidic. And we can talk about the relationships or the interactions between these things where we add a simple base like hydroxide to an organic molecule, and you worry about where we go for acid-base reaction. And you'll find now that today we'll talk about some numbers. We'll give you some sort of quantification of how acidic something is based on pKa, and you'll have to learn a range of these things to be able to solve the problems. So in this example, which we'll see again and again, we have what we describe as a strong base reacting with a good acid or a decent acid, and that's going to give us a conjugate acid on the right-hand side and a conjugate base. What we have to learn today is the properties of these left-hand side and right-hand side materials and how do they relate, which is better and which is worse. Ashley? The base has to have a lone pair at least. Quite often it's charged as a negative charge, but at least it has to have a lone pair. It's a very simple definition of a base right there. Okay? And in these first examples, the acid will have a proton. As we expand the idea into the Lewis world, and we talk about Lewis acids, not necessarily you don't have to have a proton. But right now we'll keep it simple. So these curved arrows are used to describe mechanism. And it is logical. The biggest problem in this class is people don't get onto this as soon as they can, as soon as they should. A lot of it is because they weren't prepared from chapters 1 and 2. I've got a system here in which I've got water acting as something, I've got methoxide acting as something, and I have to decide how they're going to interact. Well, I think it's logical first to think about dipoles and think about delta plus, delta minus. In this molecule over here, where do I put delta plus? On the hydrogen, right? We shouldn't be thinking about these things. They should be pretty instant now. It's on the hydrogen because the oxygen's way more electronegative and you have a dipole. So it's logical straight off that the negative piece over here should be attracted to the positive piece over there. That's why they stick together. After that, something else has to happen in order for this to obey all the rules, and we have to break this bond and push a pair of electrons to the oxygen, because we can't leave 2 bonds on the hydrogen. That would break rules. So that should give us what we call a mechanism, and that's maybe the first one we haven't seen that you've been immediately shown, but that's what we'll do. You will build this up and you'll become confident at it as you practice and as you ask questions, and you should be able to conquer very, very, very large mechanisms by the end of the second semester. It starts now. So we need to worry about how these things are happening in a dynamic sense, and then we need to worry about the outcomes. What's going to be on the right-hand side, and also how good is it, or how bad is it, and then we can measure equilibrium constants. So I didn't get to this on Monday. You've seen this before. How do you measure an equilibrium constant? Well, we're not going to do any calculations. Simple enough, right? You're going to know some numbers, you're going to know relative sizes of those numbers, and that will give you the answer. So strong acids have negative pKas, weak acids have very high positive pKas. You already know that from the past. And if you know the broad range of these things and some detail about what's in that range, you can do these problems pretty quickly. You're going to see now that the equilibrium constant, just like it was in freshman chemistry, is a sort of a measure, because scientists like to measure things, of how much of this you've got, how much of this you've got, versus how much of this you've got, and how much of this you've got. Because in any equilibrium, you've got the opportunity to go from here to here, but also, don't forget, we mixed an acid with a base, and we made an acid and a base. So there's a good chance that those acids and bases on the right-hand side can interact again and go backwards. So many of the systems you will see in this class involve equilibria. And by the time we get to the second term, you'll have to be pretty good at this so you can make decisions on the fly about whether it will be an equilibrium or not. Is the reaction reversible or is it not? This is where it starts. You've seen this reduction before. Usually water in this case would be the solvent, so we just get rid of it because it's pretty much constant. And the equilibrium constant now here, which can be described as Ka, an acid constant, is a measure of right-hand side. I'll start using these terms. Right-hand side over, or the concentrations on the right-hand side, over the concentrations on the left-hand side. That's all it is. Nothing too complicated. And you will not need a calculator in this class if you learn this properly and learn it straightforwardly. So I'm going to see that these acid constants are a bit unwieldy. They're quite difficult to work with. They start off very small, they end up very high. And it turns out it's much easier to remember and manage the derivation here, the actual log Ka, where we talk about pKa. Now again, you've seen this before, this is just my interpretation of it. And we'll see now that a low pKa, this is what you need to worry about, a low pKa or a negative pKa corresponds to a strong acid. And a high pKa means a weak acid and a molecule that's reluctant to give up that proton. Strong acids give those protons away quite quickly and quite easily. Weak acids do not. So that's the big difference right here. So yes, I mean, you need to know these things for the future. You'll need to know it for quant if you take that, for biochemistry if you take that. But I just reckon that this now, you need to understand that this is easier to learn. My pKas will go from -10 to +50, and that's it, instead of 10 to the 50 and numbers like that. So understanding that and being comfortable with it allows us to start thinking about the organic world. We have all kinds of acids that we can deal with, that we can use in the lab to do different jobs. They have different structures. But again, if you've learned the functional groups, you can start to reduce these things down into sort of fairly simple families. If you look at the top, you've already seen sulfuric acid. You know it's a strong acid. If you put your hand in sulfuric acid, what happens to it? It hurts, yeah? It hurts because it's eating your hand, right? Basically. So you could say, you know, the ouch index, as we call it. This one is a very, very powerful acid because it will hurt if you get it on yourself. Work your way up to this. This is vinegar. You dissolve this stuff in vinegar, you put your hand in some vinegar, does it hurt? It shouldn't, okay? So it's a much weaker acid. Again, on that index of ouch, this isn't so bad. So we've got this idea that very negative pKas correspond to very strong acids, which give away protons quite easily. And then as we start to go above 0 and we end into the positive regions, we get weaker acids. Now the book has condensed all of these acids that you will see in 2 semesters into this chart, 3.1. And I will reduce this down to some very simple ones that you should be aware of, and you should know the numbers. But if you want to refer in the future to pKas from the class, have a look at this chart. And it's quite complicated. There are a lot of numbers there. We don't learn them all now. We learn most of them. And we learn the concepts behind why those numbers are as they are. Why those numbers big or small or positive or negative. So I've reduced this down to here. And I think you should be spending time on this as soon as you possibly can. When I suggest, you know, learn the electronegativities, learn them. Learn the pKas, learn them. I'm going to spend a few minutes now trying to decipher what this table tells you so you have some definitions and you can recognize them, because most of this is just pattern recognition like it was for the resonance, like it was for the functional groups. We are saying now, from the last couple of slides, strong acid means low pKa, or negative. Weak acid means high pKa. Looking at this chart, there's, I don't know, 1, 2, 3, 4, 5, 6, 7, there's 8 numbers to learn. Learn them as soon as you can so you can start to do these problems. I've said this before, on my first exam, which is on the 18th, there's always a page of acid-base chemistry. It might be 18 or 20% of your grade on that first exam. If you can do acid-base chemistry, you can get those points quite easily. If you ignore this stuff, it doesn't get any better, because the rest of what we do from then on relies on this idea. And we've got to be careful with the language here, the vocabulary that we use to be able to describe acid and base strength. So I'm saying down here that anything with a negative pKa is going to hurt. Okay? It's going to protonate anything else in its presence. And we'll have to start worrying about mixing this over here with this over here and worrying about their relative acidities because they both might be acids. So you'll have to work out that the stronger one will protonate the weaker one if the weaker one can be a base and be amphoteric. Those types of ideas have become very useful. Super strong acids. The language here is a bit sort of woolly, but it does work. You know, those things are very, very powerful, and you know that coming in. They are the mineral acids that you've seen in the freshman lab: HCl, nitric acid, sulfuric acid, phosphoric acid. They're the ones that are dangerous and you have to be very, very careful of. Well, with that in mind, we can then go to H3O+, which you have seen before. If you dissolve a strong acid in water, you get H3O+, and its pKa is negative 1.7. That's a fact. You can measure this and you can see its dissociation and you can see that it's a pretty strong acid. Then we go to this, and I'll define this in a second with a second slide. Carboxylic acids. Carboxylic acids are incredibly important in biochemistry, and you'll find now that these acids are getting weaker because the pKa's became positive and they're getting bigger. But we can quantify this. You will know from now on that the pKa of a carboxylic acid in any environment is pretty much 5. There might be some subtle changes. Maybe we'll see some of that today. But a pKa of a carboxylic acid in general, when I run into you at Giant Eagle in the future, is 5. Right? It is. Now, the ones that we'll need to worry about because their structures look a bit odd, things like phenol. Phenol looks like an alcohol. But in recitation we said, okay, this is a special alcohol because it has that 6-membered ring next to it, which I'll show you in a second. And this pKa now just got bigger. And don't forget, this is a logarithmic scale, so it's like the Richter scale for earthquakes. Have you ever been in an earthquake? You know, a scale 6 is a hell of a lot worse than a scale 5, right? It's 10 times worse. So remember that as you increase by 1 unit, you're getting 10 times more acidic. So that change of units in 5 units is a big deal. That's a big difference. And we'll have to rationalize why, since this is an OH group, and this is an OH group, and this is an OH group, why do we get 5, 10, and 16? Not so difficult when we put it together, but in sort of the basics, but when you have to apply this stuff, it gets quite tricky. Moving up to water itself and the regular alcohols, their pKa's are approximately 16. Recognition of the pattern of the starting material allows you then to give an opinion of the pKa, which will allow you to do the chemistry. Alkynes, written on my table like this, pKa of about 25. That's not very acidic. You have to work to take those protons off. You have to use a powerful base to remove one of those protons, and that will be a really important thing towards the end of the term when we start using alkyne conjugate bases to do chemistry, to knit carbons together. What's that functional group, if you had to give me an opinion? It's an amine, right? So you've learned those, good. And that pK is about 38. It's getting quite high now, but we still can take off a proton from an amine. We just have to work at it with a very powerful base. Now, the worst of the lot tend to be the simple organic materials. Chapter 4 will introduce alkanes. We'll introduce simple things like CH4, CH3, CH3. They are not acidic at all. There are no bases on this planet that will take off those protons. They're just not acidic. You can make the conjugate bases by a different method, but not through acid-base deprotonation chemistry. And we'll see now that that's the sort of maximum point of the scale. That's 50, and those things are just lousy, lousy acids, in fact, not acidic at all. So what I thought I'd do to try and expand on that, you don't have these slides, but it's fairly obvious what I'm trying to do here. H3O+, fairly simple. You know this from the past. You now know that its pKa is negative 1.7. What you'll find yourself doing fairly quickly here is you'll have equations in which maybe you had to give the products, and then you have to give opinions about which side is favored based on pKa. And if you understand the pKa's, you also understand the conjugate base strengths. That's a big thing from today. Okay? Strong acid, weak conjugate base, and vice versa. So negative 1.7, pattern recognition. This is a carboxylic acid. On my chart right there, it's written as this. It's expanded to that. Make sure you're okay with that. That's a functional group you have seen before. If you just have a typewriter, that's one way of writing it. If you have a fancy drawing program like I do, that's how you expand it. That's what it is. And notice the functional group here is the carboxylic acid with the carbonyl. That C double bond O will make all the difference in the world in terms of the chemistry of this type of material. So its pKa is what? Did anybody get it from the chart? 5. Okay? Moving on, there's a phenol. pH, maybe you've seen it defined before, but now we've seen it. pH is this group when it's a substituent on something else. This is actually a molecule called phenol. You'll see a lot of this in the future. And because they have that system right here with all those pi electrons, the pK of this is going to be higher than a carboxylic acid, but lower than an alcohol. That's 10. And I'll try as we go through here to point out some of the problems that people have. That compound is not an alcohol necessarily. It's a subgroup of an alcohol, but because the double bonds are there, it is different. So I move on to this. In fact, I'm going to go back a second. I'm going to put this on the slide so you can see it. This is how detailed this stuff gets, but let's face it, engineering, clinical laboratory science, veterinary science, whatever you want to do is detailed. And if you're going to get there, you've got to handle this stuff. We're missing the pi bonds. In this case, we're missing the pi bonds. So this isn't a phenol. This is with the double bonds. This is not with the OH group. That's 16. That's a regular ROH, alcohol. Keep an eye on that one because you will get tripped up on that as you practice. The one on the right has double bonds, which will allow for resonance. The one on the left does not. Big difference. So to finish this up, on my chart I have RCCH, which can be expanded to an alkyne. In this case, later on, we'll call it a terminal alkyne, where the triple bond is at the end of a chain, and that allows for a proton to be there. And we can see now that its pKa is in the 25 region, and that's not that acidic, but it can be taken off. We do have bases that will allow this thing to come off. Last couple, what's that? What type of functional group? An amine. Now, I've had this question this past couple of days, so it's good. I'll expand on it. This is still an amine. You just have to have one hydrogen there to allow this to happen. It's still acidic with one hydrogen, two hydrogens, or three. So this type of structure here is trying to summarize that. Now, think about its pKa. It's about 36, I think, something like that. Not very acidic at all. But, again, we do have bases that will allow this to happen, and these materials becoming very, very important. Why is it not an amide? What do I need to have in here for an amide? Carbonyl. There's no carbonyl suggested here, so it's not an amide. Be careful with that difference. Last one, we'll get into this in chapter 4 very quickly, the alkanes, the idea of carbon-hydrogen bonds which are not activated. And I'll be careful how I say this. Pretty much all the carbon-hydrogen bonds in the first semester are not acidic. A lot of the carbon-hydrogen bonds in the second semester become more acidic because you add things to make them acidic. You add activating groups. But right now we're not worried about these being acidic, and the pKa here was the worst of the lot, and that was about 50. So you must know those numbers as soon as you possibly can. If I find you on campus and I ask you what the pKa of a phenol is and you can't tell me, we'll have problems. Right? Learn it as soon as you can so that we can start using them. Anybody got any questions, Ashley? Michaela? Anybody else? Who's at the back? Mr. Benedetto, are you happy? You're alive, that's a start, isn't it? Good. Very quickly, you've got to get this. This is a phenol, pKa 10. This is an amine, pKa 38. This is an alcohol, pKa 16. And notice, most of this stuff did nothing. Right? That's half the job, is to recognize that most of this stuff is doing nothing because they're all CH bonds, and the pKa of that CH bond previously was 50. So if I've got a choice of taking off one of these at 16 and taking off one of these at 50, where am I going to go? 16, the stronger acid. Not so easy to start with, but you must practice and get better at it. What's that? What type of functional group? Carboxylic acid. What's its pKa approximately? 5. So by the weekend, by coming into class next week, you should be all right with these things. You have to go bigger. You have to go to the bigger world. Most of you are biology types, engineering types. The world is huge. Look at that system. By now, you should be looking at that and going, wow, that's cool. I hope you do. That's cholesterol, very important for some of you in the future. And you've got all sorts of CH bonds happening here, and CH bonds happening here, and down there. And only one of these OH bonds. What is the lowest pKa on that molecule? 16. It's an alcohol. You will learn to focus on the business part of the molecule, where the chemistry will happen, based on knowing those functional groups and knowing those pKa's, because the rest of those protons are not coming off. You put a base in there, it's going to go after the OH group, and that's it. Now, we'll see why in a minute. It's the most polar bond. It's the most attracted to the base. And oxygen's also the best conjugate base because it can hold a negative charge because it's electronegative. Everything's coming together now. Everything's starting to come together. Molecules like that, tetrodotoxin, by the first exam, you should be able to look at that and give me some opinions about shape, about hybridization, about bond lengths, about things like whether it's functional groups, alkenes, alkynes, what have you. At the end of this, I've got an alkyne. At the end of this, I've got an alkyne. Over here, I've got a hydroxyl. Over here, I've got an NH. I quite often ask the question where I give you a big ugly molecule and tell me, or circle, the 5 most acidic functional groups and tell me their pKas. Easy points if you've done it, disaster if you haven't. So get practicing, we should be okay. Anybody want to say anything? It's getting good now, isn't it? Yeah? We're getting into this stuff now. So let's think about why this is the case. Why do we see some acids with stronger or lower pKas, and why do we have some acids that have higher pKas? If you're in clinical laboratory science, if you want to be a physician or a pharmacist, you've got to know a lot about pKa. And one of the downfalls in this class is people don't. They don't understand acid-base chemistry, they don't understand pH, they don't understand environment in a flask or in a cell. Is it acidic? Is it basic? Because that will dictate what can be allowed, what's present, what type of chemistry can happen, dependent upon the pH. So I say again, the first 4 weeks in this class are incredibly important. I think we're going to prove that soon. So we talked about pKa. We have a range of numbers. You don't know them just yet, but I'll pass them along as we talk through these slides. But what this slide is telling you is that if you know about acid strength, you also know about base strength. It's the converse. If you know about the fact that you have a really weak acid, its conjugate base is really strong, and the other way around. So those relationships now will be absolutely vital to be able to do some of these problems and do some of these questions. At the bottom I have a lousy acid. CH4 is just not acidic. Somehow we can get rid of that proton. I'll tell you how later. And you can produce its conjugate base. And its conjugate base is simply where this hydrogen seems to have given the carbon its electrons. And that gives me the conjugate base here, which is the anion. Now, if you know that the pK of this over here is 50, that's a really, really, really poor acid. In fact, it's not acidic. What that tells you is if you make this stuff in the lab, you're going to have to be very careful. That's a very, very, very reactive, if not dangerous and deadly type of material. You've got to be very careful when you use this stuff because it is so reactive. Now, you know that based on the pKa. It's the converse. We'll understand why in a second that this is the case. So the point of the slide is to say, once you understand pKa, you also understand base strength, because it's the opposite. As long as you're talking about, apples and apples, as long as you're talking about that related to its conjugate base, that works every time. So if you have a really strong acid, it has a weak conjugate base. And much of what you'll do, getting ready for this test and thinking about moving into the mechanistic stuff in the near future, is worrying about where the equilibrium lies and worrying about what can happen and nailing down what does happen based on things like pKa. Very different, this. So we've got some things to worry about. We're going to set up equations. Quite often on a quiz question, on my homeworks, what have you, you might be given this side. And you're not given any of this stuff on the right, and you've got to come up with this stuff. I'll tell you a few things right now. What's missing from this equation is Na+. You know that sodium comes along. We often don't put it in. This can be frustrating coming from general chemistry where everything counted, and you got your significant figures wrong after a 15-step equation, and you got your points taken off. Bummer. That doesn't work here. That doesn't work. So that sodium plus is not going to show in my equation here. It doesn't have to. If you want to put it in, by all means. But why am I not concerned about that? I'm a chemist. I'm interested in chemical change. Why am I not concerned about sodium plus in this equation? It's not changing. It's a spectator ion. You want to put them in? Great. If you don't, you won't lose any points for it. If it speeds things up, do it. Well, I have two chemicals. They both seem to have some sort of oxygen piece, and they have an OH possible. And mechanistically, I could argue this negative bit goes after that delta positive bit, forcing that bond to break and those 2 electrons to go onto the O. That's one way you can come up with the products. Once you've done that and you understand what the arrows mean, this means that the O over here and the H over here are bonding. And you just follow the simple rules that you've learned in the past. That's H2O. That's one of your products. And what you've done is you've forced the charge to go onto the extra oxygen over here, and you've made that. And that's it. It has 8 electrons. It's done. The question we'll have to ask soon is, can we go backwards? Because I have just produced an acid on this side and a base on this side. Once you decide it can go backwards, the question will then ask you, how far? Is the left favored? In other words, is the stuff on the left better? Or is the right favored? Is the stuff on the right better? So we'll build up, and we'll start thinking about mechanism, and we'll start thinking about simple principles. I'll get half of this done today. I'll get the rest of it done on Friday. And by the weekend, you will have a good idea about acids and bases to apply things. If you look at what's going on here, the arrow has changed. This is just a fact, and we'll fill in the detail in a second. at the top suggests an equilibrium, where the right-hand side is favored. And you think about this on the top. Which is a stronger acid, this or this, the left or the right? The one on the left, it's got a smaller number. That's a stronger acid. So then think about which is the stronger base, this on the left or this on the right? The on the left, right? It's the opposite. So you've got strong base and strong acid, and you know this already. Strong base and strong acid, which side is favored, left or right? Right-hand side. That's what that arrow is telling you. You're going to have to work it out yourselves. That's what we'll teach you to do. So in this case, the right-hand side is favored. And if I asked you what the equilibrium constant was in a general idea, is it greater than 1 or less than 1 or approximately 1? Greater than 1, because the right-hand side has more of it because it's favored. So K, I'm going to build up to this, K is greater than 1. Is that reaction endothermic or exothermic if K is greater than 1? Exothermic, right? You've gone downhill in energy. We'll start drawing these diagrams where we have energy versus the progress of the reaction, and that one is exothermic because the right-hand side is more stable. You've seen these things before. You maybe haven't had to put them together so in detail, but that's where we go. Now, down at the bottom, this is suggesting that this base, a very, very angry base, reacts with water. And if you do this, it's actually very dangerous. And it gives you on the right-hand side this conjugate acid and this conjugate base. So we now have some numbers we can learn and some principles that will allow us to understand those numbers. And we can see now, which is the stronger acid, this or this? Left or right? Go on the left. By how much? A little bit or a lot? A lot. There's a big difference in those numbers. So if you do this, it can start a fire. It can spontaneously start a flame. Because this is so exothermic that you're starting out up here on the roof, and you're ending up down there. A lot of energy given off, heat, and that thing can be flammable, that thing can be a problem. So we need to understand why. Why is that such a strong base? Why is the conjugate acid such a weak acid? And then the same sort of ideas at the top. Get this now. It is fun. So start off very simply. Once you've got some idea of left-hand side, right-hand side, acids, bases, conjugate bases, and their relationships, you can start to put equations together quite quickly. You can start to answer some quite sophisticated problems quite quickly if you're confident with this idea. So again, knowing the strength of this tells you the strength of that. Strong over here, weak over here, and the other way around. You don't know quite just yet why, but that's the case. So HCl, let's start with something simple. HCl, strong acid or weak acid? Very strong. You put your hand in there, your hand doesn't last long. This stuff now, if it loses a proton to something else, becomes Cl minus. You already know, bring this logic with you. Sulfuric acid, nitric acid, hydrochloric acid, HI, super strong acids, therefore their conjugate bases will be super weak. So over there, the idea now is that this is stable. Cl minus is a pretty good stable species. Where do you get Cl minus all the time? How do you ingest Cl minus? What's the most obvious example? Salt, French fries, food, right? You put salt on there, it'll kill you if you eat enough of it. You need it as a part of a balanced diet, right? It's not going to react with anything. It's fairly stable. So bring that common sense material with you. In terms of the other end of the scale, you're going to find that knowing the pK of this thing, which is about 50, is going to tell you an awful lot about the conjugate base strength. And also inherently tell you that that thing is unstable. On the left, the pK of 50 tells you it's not acidic. So on the right-hand side, this must be an incredibly powerful base if it's on the opposite end of the scale. And that's because it's unstable. We'll start to piece together the rules. Why do you think Cl minus is okay with a negative charge, but C minus doesn't seem to be the case? One of the rules we've already developed this semester. Electronegativity. Cl is more electronegative, it's a bit bigger, it can hold that charge better, C minus can't, because it's not very electronegative, it doesn't particularly like having a charge. So let's go. The textbook has what I think is an interesting way of presenting these concepts. If they don't organize it like this, it can be very sort of disparate and doesn't quite add up. But if you've been reading this chapter in the section here from section 3.4, the textbook will give you this list of things, a checklist to look at. And they sort of use the acronym, they go for A, R, I, O. And we'll order these things to talk about their sort of importance and how they relate to acid and base strength. So the atom, which atom's got the charge? We just did that. Chlorine's better than carbon because chlorine's more electronegative. So now we'll talk about electronegativity and we'll talk about size. Because then we have to go across the periodic table. Why is HF stronger than H2O? We have to head down the periodic table. Why is HI stronger than HBr? Those relationships should become fairly obvious. Resonance would be something that if you understood that section from chapter 2, it's a piece of cake. If you can delocalize charge, is that a good thing or a bad thing? Good thing. Delocalize it, makes it more stable. So we'll talk about resonance again. Induction, something we really haven't talked about, but if you can do a dipole and you understand delta plus delta minus, you can do induction. Very similar concept. So that will have an effect on stability of conjugate bases and also acidity of acids. The orbital, if you understood hybridization, sp, sp2, sp3, hydrogens bonded to those types of atoms have different pKas. We just showed you that on the table. Acetylene, an alkyne, has a pK of about 25, but CH4 has now a pK of 50. That's a huge difference. So that comes down to the hybridization pattern on that molecule. You'll find now that this class can become a lot of fun if you understand the basics that we just talked about for a couple of weeks, and we start to apply it. If we didn't do those things, this is no good at all. So we'll start off. I just put the words on the top left. This is the same slide you've got in front of you, to sort of clarify this and keep it organized. So we'll talk about the effect of the atom. What type of atom is involved in the bond to hydrogen, and how does that affect the acidity of the acid, and on the other side of the equation, how does it affect the stability of the base, or the strength of the base. So we just said that the pK of this guy up here was 50, right? And the pK over here is about 16. So for some reason, the one on the right is way more acidic than the stuff on the left. Understanding that, take that proton off, and go down to the conjugate base down there by doing some chemical reaction. We now have the conjugate base. If this is a super weak acid, this is a super strong base. On the right-hand side, this is an okay acid. It's not strong. 16 does not suggest a strong acid like HCl or H2SO4, but it suggests that it's stronger in this environment than the stuff on the left. So this means that this proton is easier to take off. And what does it tell you about the stability over here? Is this more stable than this stuff on the left or less? It's more. Okay? It's more. The only way you can get your heads around this to a proficient way, a proficient level, is to practice. And if you're not sure about it, come and ask questions as soon as you possibly can, because as soon as we get into 4, that's where people get left behind. So here we go. Electronegativity must be the difference here. What's the electronegativity of carbon in that molecule? 2.5. I'll find out very quickly if you didn't learn these things. What's the electronegativity of O? 3. Is it 3.5? Yeah, it's high, isn't it? So which of those two bonds, the CH bond or the OH bond, is more polar? The OH bond. I can write quite easily delta plus on this hydrogen and delta negative on this oxygen. I really can't do that to any sort of degree of confidence on the left. I don't have a big difference in electronegativities. So inherently, we're talking about the acidity of these things at the top. If I bring a base in, which is it more attracted to, the OH group or the CH group? OH group. On the left-hand side, the more positive your proton, typically the more acidic it is. That should be logical. Typically, if your proton is attached to an electronegative element, it will be acidic. If it's attached to a weakly electronegative element, or electronegativity is the same, like HH or CH, they're not acidic. It's a very simple logical idea. So I take these things off and I produce the conjugate bases. And I'll say this for the first time, and again and again and again. Acid-base chemistry, and most of the chemical reactions we have to talk about, you have to consider both sides. Here's what I start with, here's what I get, which is better, and why. So you're looking now at the conjugate bases. You've taken off those protons, and you've produced the conjugate bases at the bottom. And you now have to worry about not just the acidity of that proton at the top, but also how good is what you just made. So which do you think is more stable, O minus or C minus? O minus, why? More electronegative. That's exactly right, right? So electronegativity now is huge. So it's the first example here. The atom attached to the proton will dictate the acidity, how acidic it is. Anybody want to say anything? Sarah, you okay? Jenna? All right, keep going. So you have some trends. Periodic table, again, is brilliant. It helps you think about trends. It's logical. Atoms are related to each other across the periodic table and down the periodic table. And you can see now that as you increase the electronegativity going across from, what was carbon? 2.5? What was nitrogen? 3? What was oxygen? And, oh, it's nice and tidy, isn't it? Yeah? You should be able to get that. So which is the strongest acid, do you think? HF or H2O? HF. It's more electronegative. It's pulling charge towards itself. It's pulling electrons towards itself, which on the left-hand side with the acid will make the proton more positive. And on the right-hand side of the conjugate base will stabilize that conjugate base because it's happier having charge, because it's more electronegative. Fairly simple. So going across the periodic table, acids get more acidic. We've seen that. Well, down the periodic table changes. I'll tell you, I'm not sure you know this one, but HI is much, much stronger than HF. So now we're heading down the periodic table. HF has a pK of about 3, and I think HI has a pK of about -10. So that's way more acidic. So can it simply be electronegativity? No, because HI is not as electronegative as F. So there's something more to it. Partly it's bond strength. Partly it's the fact that this is a stronger bond because the atoms are small, about the same size. That leads to efficient overlap in the bond and a strong bond. And as you head down the periodic table, I is huge. Does not overlap very well with hydrogen, the bond is weaker. But also, as we head down the periodic table and the atom gets bigger, that helps spread the charge out in the conjugate base. So the bigger the ion, the more stable the ion typically. That might want to be written down. So on the slide here we have two examples. We have water and we have H2S. These are chosen because O is above S in the periodic table. And I've got here a pK of about 16. And even if you didn't know the pK of H2S, you could make an attempt at this because you know the principle. The pK here is about 10. We'll deal with those things later. The one on the right is more acidic, even though the sulfur is less electronegative than the oxygen. That suggests that it's not electronegativity, it's something else. So when we take off that proton and come here, and take off that proton and go there, a lot of this is to do with the bond strength here and the size of this thing. Think about this. In resonance, was it good or bad to spread things out? Good. So spreading charge out is a good thing. Do you think you can spread charge out easier on a big thing or a small thing? Big thing, there's more volume. So this is more stable because it can handle the charge better. It can diffuse that charge better. So S- is a weaker conjugate base, making H2S a stronger acid. So heading down the periodic table, you can see now a couple of trends. Heading down the periodic table, it's the size of the anion and the strength of the bond that makes the difference. So this is by far the strongest acid on that chart. And for different reasons, this is the weakest acid. So going across, it's electronegativity. Going down, it's about size. So we've covered the basics of what the atom does. In a molecule AH, A, okay, A, if it's electronegative, great. If it's large, great. It'll be acidic. Are we okay? We'll find out. So the next example, ARIO, is resonance. And this one becomes fairly obvious if you understood the material from last week. I've got two molecules that both seem to have OH groups. It's the OH group that is acidic in both of these molecules. But having just looked at our chart, this has a pK of 16 approximately, and that has a pK of 5. That's 10 to the 11 difference because this is logarithmic. That's a massive difference. So there's something happening here that makes the acetic acid way more acidic, and therefore its conjugate base way less basic than the situation on the left. They both are delta plus, no doubt. We can use electronegativity values to work that out. They're both polar. But when the base comes in and we take off those protons, we have to be careful where we go. When we do that, and we look at the conjugate bases, it reveals itself. This is how careful you have to be, because the answer isn't always in front of you. You have to dig for it and get it. Give me a term that describes this charge and versus this charge. That's good, great. This is localized. That isn't going anywhere. There are no pi bonds to send it anywhere. There are no systems that you've dealt with in the practice problems in Chapter 2 that allow you to delocalize. That is localized, and it isn't going anywhere. Okay? As opposed to this guy, where all of a sudden it's like, cool, resonance. Because everybody likes resonance. I can start pushing things around. I can draw me some resonance structures. I can draw me a resonance hybrid. And I now understand that spreading that charge out is a good thing. So let's go back a step. That stabilizes this. If it stabilizes this, it makes it what? Stronger or weaker? Weaker. If it stabilizes it, it's going to be weaker in terms of its reactivity. So that makes this stronger. There's a bit more to this. You know, those of you who've been reading the book and can handle this stuff, if I draw resonance structures for this guy, one of them would start maybe drawing that. I would draw this. I've had people in my office asking me these questions this week. Some of you don't know where my office is. Some of you don't know where Ward Beecher is. Okay. I've drawn a resonance structure. Maybe not great because I've got some charge separation, but then I can use this lone pair. And I can draw another resonance structure. And I can draw, that's horrible, here we go. I can draw this for a resonance structure from some of the practice problems in the book, and all of a sudden, my oxygen seems to have a little bit of positive charge. That oxygen with a little bit of positive charge looks like H3O+. H3O+ is pretty acidic. So the pulling of electron density away from this proton is more of a deal in that molecule than it is over here because I can't delocalize those electrons. So again, both sides. This proton is a little bit more positive because of the pulling away by the carbonyl, and on the right-hand side, or down here, this molecule is more stable because of delocalization. Subtle, but key. You all look completely happy, for lack of a better word. Bailey Choma, are you happy? Sure. Okay. Sure. We need to be yesterday, right? This is the foundation of where we go next. You can't handle this, you can't handle any of what's to come. Right, we draw resonance structures, we talk about localization versus delocalization based on a principle from chapter 2. We're done with chapter 2, we learned the chess moves, we're putting the chess moves together to play the game. Same idea here, conjugate bases will be stabilized by resonance. If you can't do resonance, you tend to be less stable, and that equates to more reactive. I think we've seen that before. So the last one. No, I've got 2 more to do. Induction. Induction is something you haven't really thought about before, but it's something that's logical if you understand dipoles. If we think about here, the pK of this guy is 5, and I think the pK of this guy is about 2. There is a difference. The one on the right is more acidic. And the reason we could argue it's more acidic is the presence of the chlorines. We have swapped out hydrogens from this molecule, and we have made it more acidic. So it's all about electronegativity, right? Electronegativity of Cl is 3, and there are 3 of them. So which direction will the bond electrons go towards, the Cl or the C? The Cl. And I can draw little arrows here to show that those chlorines are kind of hogging the electrons in the CCl bonds. So that maybe says that this carbon here is somewhat positive. Well, that's not happy. It wants electron density, so it will pull electrons away from its neighbor. And that will not be happy, so it will pull electrons away from its neighbor. And guess who loses out? The hydrogen at the end. So the proton in this molecule is a little bit more positive than the proton in that molecule because of something called induction. Basically, single bonds in which you have polar components and you have electronegative pieces pulling electrons away from something else, induction. In this case, we're going to see now that, again, you have to worry about the right-hand side. You have to worry about the conjugate base because the conjugate base now will also be stabilized by that induction. I'm going to take a second here to talk about this. This is resonance stabilized, and this is also resonance stabilized. So it can't simply be resonance stabilization that makes them different. It has to be the presence of those chlorines. And if you have a 10 to the 3 difference in their acidities, that's significant. Based on electron delocalization or electrons being spread out. This is delocalization, we know that. But induction is similar in the sense that you're spreading electron density through single bonds. Delocalization typically through pi bonds, induction through single bonds. They can build up and they can work together to give you stabilization. So the inductive idea now, if you see close by to your acidic site some electronegative elements, they will have something to say about the acidity close by. If you were to take this and you were to put the chlorines over here, let's say the carboxylic acid had this structure and the chlorine was over there, do you think it'll have much of an effect? No, it dies off. Right? It dies off as you go further away. But local, very close, you'll certainly have a difference in the pKa. So induction now, we'll finish off with the orbital, and that'll get us to a good place for today. I'm done with acids and bases on Friday. As soon as we come back next week, I'm into chapter 4. So again, we're not here Monday. It's incumbent on you to get this stuff worked out because it's a big chunk of your first exam. And that first exam is the most straightforward exam you'll ever get from me. Of the 8 exams that you will take, the first one is cake. Eat the cake. I'm hungry, yeah, all right. Let's look at the idea now of orbitals, this idea of what the orbital makes a difference. Because on my chart, I had alkanes, you don't know the names yet, but it's an alkane, and that had a pK of 50. That's a lousy acid, it's not acidic at all. And then we had ethylene in the middle, CH, we have an sp2 hybrid carbon, and its pK goes down to 44. It wasn't on my chart, but there's the number. And acetylene, which was on my chart, 25. That's a massive difference. From 50 to 25 is a huge difference in the relative acidities of those molecules only by simply having CH bonds. All of a sudden, this CH bond is not acidic. All of a sudden, this CH bond is potentially acidic. So it's carbon. It's carbon is carbon. unless you dig a bit deeper and recognize that the hybridization pattern here is what? sp3 and the hybridization pattern there, sp2 and the hybridization pattern there, sp. So the last thing for today, all that's changing is the hybridization pattern in the carbon attached to the proton. So we're now saying that sp3 H bonds are not acidic yet, sp2 H bonds are more acidic, and sp H bonds are reasonably acidic. So what's it to do with? It's to do with how much S character you have in the orbitals. In an sp orbital, how much S character is in there? 50%. In an sp3 orbital, how much S character? 25%, less. The more S character you have, the more electronegative you are. When you go in atoms, the same atoms, you're dealing with their electronegativities, dealing with their hybridization patterns, the more S character you have, the more electronegative that atom, which makes sense. Which are closer to the nucleus, S or P? S. Which will be held more tightly, S or P? S. So S could be said to be more electronegative, right? They're held more tightly. Same idea. So the more S character you've got, the tighter those electrons are held, which means when I take off these protons and I put that charge in an sp orbital, it's going to be more stable and held more tightly than if I put it over here in an sp3 orbital. That probably meant nothing. Read it. That's where I'll start on Friday, and then we'll do some problems. Ms. Clark. Okay.
So if I like, does one of these holes, without